Hello, this is workbook 3G and H. Just going to push through no matter how long it takes and get this finished. I'm going to start with a free body diagram. There's a coin on a table. It's like an old record player or some such, and it's spinning around. We want a free body diagram. The force normal up and the force of gravity down should be balanced. This coin's not going up and down through the record player, and then there's a force of friction pointing inward. Because if there were no friction, what would the coin want to do? Well, the coin would want to slide off the record player, right? Whoop, it would just slide right off, but it's not. It would slide out and off the record player. So just get out your record player and try that. Starting from the equation, an inequality has been derived that must be satisfied at all times. If the coin does not slip on the surface, of derivation has been done for you. You must fill in the annotations to explain each step. All right, well, the first step is, I'm just going to talk through it. This is the formula for the force of friction, that the force of friction is less than or equal to the coefficient of friction times the normal force. That's the definition of friction. The coefficient of friction, mu, this letter right here, that's just a property of a material which tells you how sticky the two surfaces are. So it depends on what the two, so coin and turntable have a specific coefficient of friction between them. And normal force, of course, we know what the normal force is. It's the force perpendicular to a surface. Sometimes it's equal to the force of gravity. In this problem, it is equal to the force of gravity because we're not on a ramp. So that's the next step is replace the normal force with weight because they're equal to each other. And then the next step says, well, what's the friction? There's a centripetal force because it's spinning, because there has to be. And so the force of friction is what's creating the centripetal force. So we replace the force of friction with the centripetal force. That's why we did that. And then the mass cancels here. So mass is canceled. And then what do? We multiply both sides by r. Multiply both sides by r. And then we take the root of both sides. And then the next step is the weird one. So it turns out that, where did that come from? Why did we even bother taking the square root? I don't know. But, wow, so then they jump all the way down, substituting 2 pi r over period for the speed of the coin. So the velocity is the distance over the time. So where does this come from? Well, the distance is the circumference, and the time is the period that it takes for the coin to go. So what we did is they just squared that. They just said, okay, 2 pi r over t is equal to the square root of mgr, right? And so that if we squared everything, you get a 4, 2 squared is 4, pi squared is pi squared, and then t squared, you squared, it's t, and then you have the mu g, and then that goes away, and then you have mu gr, and over here, so then you have r squared on this side and an r on this side, and that r cancels one of these r's. And that's why the r isn't squared. And so that's how they got there. So that's what they wanted you to do, is explain how they got from the top to the bottom. All right, Blake and Carlos are trying to predict whether the coin will slip if the coin is too close to or too far from the axis of rotation. That would be the middle. So what do you think? I don't know. But you probably already figured out. I'm looking at the answer key as I do these so that I don't hem and haw and look stupid. All right, Blake. I think the coin will slip if it's too close to the axis. It is like if a car takes a turn too tightly, the car can slide out of control. There's not enough force if the radius is too small. I think the coin will slip if it's too far from the axis. It's like a merry-go-round. If I ride a merry-go-round near the center, I don't feel much force pulling me to the outside, but if I ride near the outside, there's more force pulling me away from the axis. State whether the inequality written in Part B provides support for that statement. If so, explain how. If not, explain why not. Ignore whether the student statement is correct or incorrect for this part. Okay, because I was going to go Carlos on that. The inequality written was, let's review, 4 pi squared r over period squared is equal to mu g. All right, so mu is constant, g is constant, the period is constant, right? Because no matter where you are on the record player, whether you're at the middle or on the edge, it's going to take you the same amount of time to go around in a circle. Even though the circles get bigger, the amount of time gets smaller. I mean, the amount of time stays the same. Oh my God. Right, so as r increases, what has to happen for it to be balanced is if this, so nothing changes, right? G doesn't change, mu doesn't change. So as r increases, this side gets bigger, and then at some point r is going to get so big that it's going to overpower this side and it's going to slide off. So really, Carlos's statement is supported by the equation, and Blake's statement is not supported by the statement. And so actually, so the coefficient would have to get bigger in order for the coin not to slide. Of course, the coefficient can't get bigger. It can't change unless you change what the things are made out of. State whether the coin will slip when it's too close or too far. I'm going to go with too far. And they're arguing about the mass. So the mass was canceled out in the derivation, and so the mass doesn't matter. The mass, the force that causes the motion is proportional to the mass, and the force increases the same way as the resistance to the force. So the motion will be the same independent of the mass, is what the answer key says. Let's go on to 3H. Now we have, oh man, I hate this ride. Have you ever been on this ride? This is that ride where you get pinned up to the side as it spins around, and then somebody barfs, and the barf flies around and hits everybody. Oh my God, I hate this ride. Anyways, let's do free body diagram. You know, it's the same free body diagram as the last thing, except that, well, it's kind of the same. Actually, it's completely different, honestly. This part's the same. There's a force of gravity. There is a force going this way, and there is a force going this way. But what are those forces? Well, it turns out that this time, this one is the friction, and this one is the normal force, right? Because the normal force is pushing on the person. The friction is keeping the person from sliding down. Gravity is pulling down. Derive an equation for the normal force on Carlos after the floor has dropped out. For each line of the derivation, explain what was done mathematically. Annotate your derivation. Explain your answer in terms of m, v, and r, and physical constants like g as appropriate. All right. And they only give us 2 boxes. How about that? So in the horizontal direction, the net force is equal to ma, right? And the only force horizontally is a normal force pushing on him, so the net force is the normal force, and that's equal to the m times a. The a is centripetal acceleration, so that's the formula for the normal force. It's the centripetal force formula. On the next ride, Carlos takes a force sensor and places it between himself and the wall of the ride and collects the following data about the force from the wall and the speed of the ride. Cool, Carlos. Which quantity should be graphed to yield a straight line whose slope could be used to determine the radius of the ride? Justify your answer. You may use the remaining columns in the data required out of the table. All right, so we have this equation here, and we need to make a graph that gives us a straight line, a linear line. What quantity should be graphed to yield a straight line for the slope? All right, so what I see here is that if I rearrange this equation, use darker color, so I could say the normal force times r is equal to m v squared. So the mass is a constant thing. It doesn't really matter. And so this is kind of like y equals mx, right? So the slope would be that, and this would be the x variable, and this would be the y variable. So what we want to graph is the square of the speed, and that would be 25, 64, 100, 144, 15 squared. Come on, give me a break. What am I, some sort of freaking calculator here? Okay, I'm going to go 225. I got it right. It was 225. Good guess. All right. Okay, so which quantity should be graphed? Yield a straight line, b squared. Plot the graph. Okay, I'm not going to look up the answer because I don't need to copy that. Oh boy. Now that's a freaking mess. Okay, maybe I will copy it. That sounds like something the teacher should have prepared ahead of time. All right, and so if you graph the data, you get a graph. Let's see, so this is the force, Luke, and this is the v squared on this axis, and that's 50, so that's 150, and that's 400, and that's 6, so this 800, that's 1200. So that just gives you a frame of reference. That's 2000 up here. So they found a data point about right here and somewhere in this area right here and somewhere about right here. And you can see getting a nice little linear line here. And then they had one up here about like that. And they got a nice line that looked like that. That's what the answer key shows. Using the slope calculated in part D, determine the radius of the right. Oh, so now we need to find the slope of the line. And I like finding the slope of a line by picking 2 points off of the straight line. Of course, that is a crappy straight line. But there's a point right there, 0, 0. And then there's a point right there, which is 200 on the bottom and 1600 on the top. So that looks like about 8. The slope is about 8. And the answer key got 8.5. So that's pretty close. Pretty good. Good enough. And that's it. We're done. Oh, no, there's a question. Determine the radius is 50 kilograms. Oh, yeah, because you have to. So the slope was 8.5. And then we had to put it back into the equation. So we weren't finished. It was, what was that equation? Fn Rm v squared. So Fn R m equals m v squared. So he said the mass was 50 and the slope was anyways, this was 1600, no, 200, and this was 1600, and that was R. And there you go. They got 6 meters. What did I get? I don't know. 50 times 200 equals, divided by 1600, 6.25. Hey! Pretty good. All right. I amazed myself. All right, that's it. That was the week. Finally, we're done.